We've spent some time already talking about functions, in particular linear functions. In this section, we'll look more at graphs of functions and how we can graph certain famous functions and their transformations. So in your book, you can see all of these pictures that you see here that talk about how to graph vertical shifts of a given graph, horizontal shifts, reflections, etc. So look for these in your book. I'll just go over a summary and then we'll do some examples. So if you have a graph of a function already, let's say f of x, then you add something to it. So we're assuming c is positive in all of these descriptions. If you add a number to the function f of x, it shifts the graph up c units. If you subtract a number, it shifts the graph down c units. Now this may seem a little counterintuitive with adding and subtracting numbers inside the parentheses. So instead of adding or subtracting something to the whole function equation, you just change the x. You'll evaluate f of x plus something or f of x minus something. And you might think x plus c means you go to the right c, but no, we go to the left. We'll talk about that. We'll look at some examples. And f of x minus c makes the graph go to the right. If you put a negative in front of the whole equation, basically distribute the negative to everything in your equation, that just flips your whole graph over the x-axis because all the y's change to their opposite values. Positive y's become negative and negative y's become positive. That in effect flips your graph over the x-axis. If instead you change all the x's to negative x's, now all the positive x's change to negative, all the negative x's change to positive, so that's going to flip your graph over the y-axis. And then if you put a number, and we're still looking at positive numbers, in front of your whole function equation, multiply everything by a number, then it depends on whether that number is bigger than 1 or less than 1, but still positive. If the number you put in front, like if you multiply everything by a 2, if it's bigger than 1, it stretches your graph vertically. All the y values are going to get multiplied by 2. So you can see if a y value was positive, it becomes more positive. If it was negative, it becomes more negative. It stretches everything in the vertical direction. If you multiply by a number that's less than 1, it shrinks it vertically. All the y values get halved. So we'll look at a couple of examples of these, and you can find more examples in your book. In this first example, we have a graph of two different functions given, and in each case, we want to graph these transformations. So first you have to see how is the function that you're writing here different from your original f of x. We are adding 3 to the whole function. All the y values get 3 added to them. So that means all the y values will get bigger. So pick some key points, like maybe I would pick this point right here and look at its y value. And then shift it up 3 units. Plus 3 means everything is going to go up 3 units. So that's going to look something like that. Then pick this key point over here and shift that one up 3 units. That looks something like that. Similarly, this one is going to come over here. So if I just connect these points, it's going to have the same basic shape. Everything is going to be pretty much parallel to your original graph, but everything got shifted up 3 units. Maybe I'll shift the x-intercepts too. That is going to go over there, and then everything is going to go higher by 3 units. This one goes up over here. And this is the graph of f of x plus 3. Everything got shifted up 3 units. In the next example, we have to graph f of x minus 2. So this is a different function f of x graphed here, and we want to graph the new function y equals f of x minus 2. Now all the y values are going to go down 2 units. Subtract 2 from all the y values on the graph. So for example, the y-intercept is going to go, looks like over here. And then maybe pick some other key points, maybe this local minimum. It goes, oh, I don't know, about over here. And then this local maximum is going to go about maybe over here. So you get a graph that looks roughly like this. I'll bring this one down 2 units also. And I'll bring this one down 2 units. So something like this. Everything got shifted down 2 units. So these are vertical shifts. You'll get some practice with that. In the homework, you can also look at more examples in the book. To demonstrate horizontal shifts, I'm going to use a graphing calculator to look at the graph of 3 different functions. They're all related to the function x squared. Actually, I can also demonstrate what happens when you multiply by the number 3 here. If I just graph y equals x squared, so we will look at the graph of y equals x squared, just in the standard window. That's the graph of y equals x squared. It's one of the functions you have to remember the graph for in this section. It's a basic parabola. And then 3x squared, if you just compare it with that, so I'll do that in y2. You can see what happens. All the y values get multiplied by 3, so there's a vertical shift there. But really, I'm more interested in these functions, so you can see horizontal shifts. I'm sorry, not the vertical shift, I meant a vertical stretch. So we did stretch it vertically, comparing the graph of x squared and 3x squared. It didn't shift up, it didn't translate up, it just got stretched. So let's get rid of that first graph. I'm going to deactivate that one. And let's look at the graph of a g of x. 3 parentheses x plus 5 squared. We'll look at that in the standard window. Now, if you remember, we said when the number is right next to x, so this is really f of x plus 5. You just replace x with x plus 5. It's a horizontal shift. And intuitively, you might think that it should go plus 5 units to the right, but let's see if it does that. Oh, look at that. It shifts 5 units, 1, 2, 3, 4, 5, to the left. So you can see when you have plus a number inside the parentheses affecting the x. So you have to apply that to x first before you perform all the other operations of the function. Then it shifts it to the left. Let's see what h of x looks like. So here I put 3 times x minus 9 squared, and now let's look at the graph of the new function. Oh, actually, we might not see all of it, but you can see because it went 9 units to the right. So keep this in mind, and this should clarify that rule that if you have x plus c for the new input, then that shifts everything in your graph c units to the left. X minus c shifts everything c units to the right. So here's a graph of some function given. This is the graph of f of x. We want to graph f of x plus 2. So hopefully with practice, you will remember the difference between having a plus 2 at the end or the plus 2 inside the parentheses next to x, or maybe even 2 times f of x. These are all different transformations. So right now we want to do f of x plus 2, which is a horizontal shift. Everything moves 2 units to the left. So pick some key points. This point over here is going to go here. This point is going to go here. This local maximum looks like it's going to be somewhere over there. And then this one is going to go over here. And I should also do the x and y intercept. In this case, it's the origin that goes over there. And then it's the same shape as your original graph. It just got shifted. Now, if you're curious why it goes to the left when you have plus 2, just look at one of the points on the original graph, like this one right here. When x is 5, f of x is 1. f of 5 is 1. But in the new graph, to get 1, x has to be 3. It has to be 2 less, so that when I add 2 to it, I get the same y value. That's why we move the graph to the left when it's plus a number inside the parentheses. So in previous sections, we've already looked at linear functions pretty extensively. There are other functions whose graph you should know. Power functions, any function that can be written as x to a whole number power, well, really powers 2 or bigger, x squared, x cubed, x to the 4th. You should have these basic shapes in mind. You can graph them in your calculator first and then just commit them to memory. X squared is a pretty famous one. You know, that's the parabola, a quadratic function. X cubed is the basic cubic function here. It goes for negative x's, it's negative. For positive x's, y is positive. That's how it's different from x squared. It kind of has that flattening out at the origin. The graph of x to the 4th looks a lot like the graph of x squared, but it's a little flatter at the origin. The graph of x to the 5th looks a lot like x cubed. In fact, all the x to the even powers look similar, and x to the odd powers look similar to each other. Then we also have root functions, nth root of x. I would say definitely at least remember the graph of square root of x and cube root of x. Now remember when we were talking about domains of functions, we said that domain of square root of x is where inside the square root is greater than or equal to 0. That's why this function is only defined for x is greater than or equal to 0. But domain of cube root of x is all real numbers. That's why this function is defined for all the values of x. Any even root looks very similar to the square root. Any odd root looks very similar to the cube root. And in fact, they're sort of the flip side of, it's like sideways versions of the power functions. So if you look at your book, there's all this list of the different functions you should know. I'm not really going to talk about the greatest integer function. I won't hold you responsible for that. But you should have a good idea of the basic shapes of all of these functions that are listed in your book. This is like your library of functions for basic graphs. Any line, x to any power, whole number power, any nth root of x, reciprocal functions, at least 1 over x and 1 over x squared. You should have a good idea of what those graphs look like. And of course, absolute value of x, which we have talked about before. So you should know most of these, the ones that I talked about. And then know how to graph their transformations. So let's practice with just the x squared. So here's the graph of f of x equals x squared. We have graphed a bunch of functions, but we used what I called the most primitive method to graph them by just making a table of values. But now we're going to make it a little bit more sophisticated. So first you can use the primitive method to make sure you understand why all of these graphs look the way they do. But then we'll use our knowledge of transformations to graph all new kinds of functions. So here is a list of functions. These are all transformations of x squared. And here are a bunch of graphs. There are 8 functions and 9 graphs, so one of the graphs is not going to get picked. What I want you to do now is pause the video, look at these equations, look at all of these functions, and look at all of the graphs and try to match them. So these are all transformations of y equals x squared, which is just your basic parabola. So for example, for the first one, I would just look at the function and then see which graph matches it. For the first one, what are the transformations that happen here? Order of operations holds here too. So inside parentheses first, look like we added the 2 to x. Remember, that is a horizontal shift 2 units to the left. So this graph, with everything would shift 2 units to the left. And then it gets multiplied by a negative. That's a reflection through the x-axis. So then it gets flipped over. So which of those graphs looks like that? You would pick the correct letter and then put it over here. So to the left and then flipped over, that looks like the graph in part G. So try to do these all on your own and then come back and check and see if we agree. This is how I match the functions with the graphs. Do you agree with my choices? So remember, the number inside next to the x affects the graph in the horizontal direction, moves it right or left. Then if you have a number outside being multiplied, it is going to either stretch it or shrink it vertically if it's a positive number. Same thing if it's a negative number, but it gets flipped upside down. It flips over the x-axis. And then that number at the end that gets added or subtracted to the whole final y value shifts the whole graph up or down. So let me know if you think I did any of these incorrectly or if you have any questions about them. So if you remember the graphs of all of your basic functions, and then remember also the transformations and how the graphs get affected by doing things to the equation of the function, adding numbers to the whole thing or to x, or multiplying by a negative, then you can graph any of those transformations of any of those basic functions without plotting a bunch of points, not making a whole bunch of table of values, but by just using transformations. So we are going to describe what function we would start with, what standard, one of those famous functions, and then what transformations we apply to graph the given function. For this one, we are going to start with square root of x, and then we will follow order of operations. That plus 2 is inside the square root. We have to take care of that first. So that's like doing an f of x plus 2, which means then we have to shift it 2 units to the left. And then the plus 1 at the end means we have to shift that new graph 1 unit up. So we start with square root of x, which you should know roughly what that looks like. It's going to go through 0, 0, 1, 1, 4, 2. I know it looks like I'm doing table of values, but that's just to remind myself what the graph of y equals square root of x looks like. Then we are going to shift that 2 units to the left, so every point goes 2 units to the left. And that's going to look like that. And that's going to shift 1 unit up. So everything goes up 1 unit. And it looks something like that. Now I'm just doing a rough sketch there. I'll get rid of my original, whoops, didn't mean to erase that. So let's see, 2 units to the left and 1 unit up. Everything moved 2 units to the left and 1 unit up. So this is the graph of square root of x plus 2 plus 1. Let's do one more. We will, and you have to describe your steps just like I'm doing here. We start with, what basic function do you think we should start with? We'll start with y equals absolute value of x, which just looks like this. And then order of operations says take care of that x minus 2 inside of absolute value first. So we will shift to the right 2 units, 2 units to the right. And then we have to take care of that -3. So that is going to be a vertical stretch by a factor of 3. So all the y values get multiplied by 3, but then that negative means you're also going to flip over the x-axis and finally shift the whole thing 4 units up. So I'm going to do a quick rough sketch and then I'll make my final sketch a little bit more careful. So here's the graph of square root of x. Then we have to shift it 2 units to the right. It looks something like that. Then we have to multiply it by a -3, which stretches it vertically and also flips it over. So something like this. And then shift it 4 units up. So 1, 2, 3, 4, something like that. But that's a big mess. So let's clean that up. I know that the shape of my graph is going to be an upside down V and thinner, narrower than a regular absolute value of x. And so we started at 0, 0. We moved 2 units to the right, multiplied by a negative. That doesn't change the y value there, a -3, and then move it 4 units up. 1, 2, 3, 4. So the edge of the corner of my V, upside down V, is over there. And if you just follow, we multiplied everything by 3, we flipped it over, we get something like this. So as long as you describe the steps correctly and you have the right shape of the graph, you'll be fine. So we're sort of going in the other direction in this problem. Instead of giving you the transformed function, we say if we are going to apply these transformations, what would the new function look like? So if we start with f of x equals x cubed, then shift it 2 units to the left, and then reflect through the x-axis, what would that new function equation be? So 2 units to the left, that's a horizontal shift that affects x before we cube it. It moves it 2 units to the left, and that happens when we have x plus 2. and then reflect through the x-axis, that just means the whole thing is going to get multiplied by a negative. In the next one, we start with square root of x, stretch vertically by a factor of 4. That means the whole thing is going to get multiplied by a 4. And then shift down 3 units. That means then the whole thing has to get 3 subtracted from it. So you will also practice doing these. So we're going about this from different perspectives. Given the transformation, write the function. Given the function, figure out what the transformations are and graph it. Given the graph of a function, perform the transformations. You're just going to practice it in a lot of different ways. Lastly, in this section, there's another property of graphs that we want to discuss, and that's symmetry. Some graphs have a certain kind of symmetry. They are symmetric to the y-axis. So that means basically the y-axis acts like a mirror. Everything on the right sees its mirror image on the left. The graph is kind of like the y-axis is cutting it exactly in half. Those functions are called even functions. The definition of an even function is if you replace every x with negative x, you get the exact same function. Some functions are odd functions. For odd functions, if you change every x to negative x, you get the exact opposite of the original function. So in order to determine whether a function is odd or even, well, if you have the graph, you just have to see what kind of symmetry you have. If your graph is symmetric with respect to the y-axis, it's an even function. If it's symmetric with respect to the origin, and I'll talk about what that would look like, then it's an odd function. But how can you tell by looking at the equation of a function whether it's odd or even? In order to decide whether a function is odd or even, because of the definition, you have to find f of negative x. What does that mean? You've heard me say this before. If you want to find f of anything new, make a blank template, and then you're going to replace the parentheses, fill them in with the new stuff, in this case, negative x. So what do we get? We get the cube of negative x, which is negative x cubed, minus negative x plus x. Well, obviously, this is not the same as the original function, so this function is not even. Let's see if it's odd. A function doesn't have to be even or odd. It's not like integers. It could be neither. So we do have to investigate both. It's not even. To see if it's odd, let's also find negative f of x, because you see that in the definition of odd functions. F of negative x has to equal negative f of x. What does negative f of x mean? It just means you multiply everything in your function by a negative. And when we do that, we get negative x cubed plus x. Oh, and look at that. They are, in fact, equal. F of negative x turned out to be equal to negative f of x. That means the function f is odd. And that's where the name comes from. All the powers in this polynomial are odd, and when that happens, you get an odd function. How about this function? So remember, in order to decide whether a function is odd or even, given its equation, you have to find f of negative x first. And that means replace all the x's in your function with negative x and see what you get. So negative x to the fourth power is positive x to the fourth, because negative to the fourth power is positive, minus 4 times negative x squared gives you just x squared, minus 2. Oh, and look at that. That's exactly equal to f of x. If f of negative x equals f of x, just by definition, that means the function is even. And if you look at this polynomial, it is a polynomial, all the powers in that polynomial are even. That's why that's an even function. Now, a function, it's not only polynomials that we characterize as odd or even. It could be any function if it just satisfies the definition. If you take trig, you know you will study trig functions like sine of x and cosine of x, and you'll learn that, for example, sine of x is an odd function and cosine of x is an even function. Let's do one more, and you might want to try this on your own first and then check back and see the work. We have to find f of negative x, so that means I will replace all the x's with negative x. So what do we get? Negative x to the fourth power is just x to the fourth power. Negative x becomes plus x. That is not the same as the original function, so we know it's not even. Is it odd? Let's see. Let's find negative f of x. That's the negative of the whole thing, so I have to distribute that negative. Oh, they're not the same. So f of negative x is not the same as f of x. It's not the same as negative f of x, which means this function is neither odd nor even. It doesn't have any kind of symmetry with respect to y-axis or with respect to the origin. Now, if you want to see exactly what the graph looks like for odd and even functions, we can look at some of these famous functions that you have to remember. And this will kind of also tell you where the name odd and even comes from. If you look at the graph of x squared, you'll see that it's symmetric with respect to the y-axis. Any point on the graph, if it looks at the y-axis as a mirror, it sees its reflection exactly on the other side. Now, for the odd-powered functions like x cubed, it is not symmetric with respect to the y-axis. It is symmetric with respect to the origin. If you pick any point on the graph of y equals x cubed and then go to the straight to the origin and then go out the exact same distance, you land at another point on the graph. So the graph of y equals x cubed is symmetric with respect to the origin. So make sure in this section you review and make note of all of those transformations: vertical shifts, horizontal shifts, reflections, stretching, and shrinking, how we can graph the transformations, all the different things that can happen to the graph of a function, and all the basic graphs that you have to remember from now on without having to make a table of values with a lot of points. You'll just remember the basic shape of these graphs. Or using your graphing calculator, you should know how to graph these. And then applying multiple transformations to a function to get a new graph. Horizontal shifts, vertical shifts, reflections, stretching, all of that stuff. How to graph transformations of your basic functions by stating exactly the steps. What basic function do we start with, and what transformations do we apply to it to get the graph of this desired function step by step in the correct order. And finally, odd and even functions and what it means in terms of the symmetry of the graph of a function.